All right. Hello, everyone. Louder. Try that out. Yeah, that's not bad. All right. So today we're switching gears and going to be talking about chapter 13 stuff. Right. So we're out of chapter 12, which was a lot of the algebra and whatnot of three-dimensional space. And we're finally getting into a bit of calculus today. So that's exciting in a calculus course. I guess before we get into that, a few admin things, right? Well, we have a quiz tomorrow, our second quiz. That's going to cover 12.5 and 12.6. So again, the stuff up until Monday's class, so that was 12.6. And the last quiz covered up until 12.4. So 12.5 is the first section. Remember, that was a big one. Had a lot of lines and planes, and there was a lot of different types of questions that we could ask, as you saw in your web work homework. That was a big set there. So make sure you're reviewing that. And then 12.6, maybe a bit more straightforward. We practice that technique a lot in class of doing different cross sections and whatnot, graphing those. But those are the two main topics that'll be on your quiz tomorrow. Other than that, I can't think of any other administrative stuff. I guess sooner or later, we're going to have to start thinking about the exam that's next week. And so you should have that in the back of your mind, starting to come up with a study strategy and whatnot, how you're going to divvy up your time and when you're going to review what. Next week, we will have a day, Wednesday's class dedicated to review. I have posted in D2L a review sheet that I'd like to maybe cover on our review day here in class. And I also put a kind of, basically it's just a checklist. It's a knowledge checklist. It kind of goes over the main topics from each section. Just that way you can kind of read through them and kind of verify, hopefully you say, yes, I'm good at that. Yes, I'm good at that. Right? No, I need to study this a little bit more. But maybe I can showcase that as the exam gets a little bit closer, maybe in Friday's class and Monday's class and whatnot. So just a heads up, though, that those are available on D2L now. All right. Questions about really anything before we get into the math? So I see one here. Yes. Yeah. It'll follows the same sort of format, right? So the test is on Thursday. It'll be kind of everything up until the Monday before class. But then Wednesday's a review. So, I mean, we're not learning new material in Wednesday's class. And then Thursday, you'll have your recitation. That'll, again, be kind of a review to kind of make sure you're prepared. And then Thursday night, you'll take the test. But yeah, all of chapter 13 stuff is fair game for that. Good. Any other questions? Down. All right, then. Well, why don't we talk about the math? So again, jumping into chapter 13, 13.1, it does deal with a lot of the algebra of vectors and vector functions in space. So now basically I want you to think of this as an upgrade from 12.5. In 12.5, of course, we talked about lines. We also talked about other stuff, mainly planes, but we talked about lines. And lines were a special type of vector function, some sort of curve in space, right? And so now in 13.1, we're going to be talking about, rather than just good old linear stuff, what if you have other functions here, right? For instance, you can make a helix and all sorts of interesting curves in space. Then we can talk about, I mean, we can, you'll see in web work and whatnot, they ask you about intersection problems and that sort of stuff. And we can build up the calculus just like we did back in calculus 1, right? So you can start to deal with taking derivatives and integrals and all that sort of stuff. And that's the main idea of 13.2. And so that's kind of why they're combined into one class here today. So, but here's some of the limit stuff, for instance, that we saw again in the pre-class video. So we're building up the calculus for these vector valued functions. So that's the pre-class stuff in a nutshell. Any questions before we jump into the new stuff for today? Yes.
Starting with like a few derivatives, are we gonna like, are we gonna start like, are we gonna get straight doing like some of those really hard derivatives like you did towards the end of Calc 1 and 2, or is it gonna like continue to be like the easier ones that we saw right now?
So the question is about, I guess, the difficulty level of derivatives and antiderivatives that we're likely to see here in Calculus 3. I mean, there will be some challenging derivatives and antiderivatives here and there. But some of that stuff really is a better test of your calculus 1 and 2 skills rather than trying to do it in 3 dimensions. And so we have to be careful whenever we're writing quiz and exam questions and also homework questions to some extent, right? That the focus ought to be on the calculus 3, not on doing a really good calculus 1 or a good calculus 2 problem. That being said, so usually a common question that will come up, and especially because we're starting on the calculus here, you know many techniques from calculus 2 of integration, right? Maybe from calculus 1, you know things like U substitution, but then starting in calculus 2, you learned about integration by parts, you learned about partial fractions, you learned about trigonometric substitution, right? You have many different techniques now of integration that can be applied. And in a class that's, testing you on your integration techniques, right? That makes a lot of sense to cover all of those. So the question that usually gets asked is, which of these will appear in calculus 3, right? And I would say that it's pretty rare for us to have anything about like trigonometric substitution or partial fractions in the class. So you don't see a lot of those. Definitely a good amount of U substitution. U substitution is kind of like in the Goldilocks zone where it's maybe not too time consuming. And every once in a while, you will see an integration by parts style problem. Integration by parts gets picked up with a vengeance in calculus 4. And so it's really doing you a favor not to let you lose those skills completely here in calculus 3. So although it doesn't maybe serve our purposes as much as we need it to, we don't want you to forget about integration by parts. And so that's kind of why, you'll see that more in the homework problems, maybe some integration by parts. I can't think of a lot of quiz or exam problems that have integration by parts because, again, that's more focused on calculus 2 rather than calculus 3, which is really visualizing things in 3D. So, all right, any other questions? Okay, so then why don't we go ahead and switch gears here. Oops. And so I want to talk a little bit about the pre-class videos left off with limits. And I would like to get into derivatives and integrals for our vector functions. So if you have a vector function, right, that means it has components. There's an x component, a y component, and a z component, most of the time here in calculus 3. And if it's differentiable, which just means that it makes sense to take the derivative of it, right? Not all functions that turned out from calculus 1 are differentiable. But if it makes sense to take derivatives of this, then the derivative of this vector valued function is exactly what you would guess it to be. That is, you take the derivative of the first component, you take the derivative of the second component, you take the derivative of the third component, you put them exactly where they live, all inside of some brackets, right, denoting a vector here. So this is how you take derivatives of a vector valued function. You just go term by term, taking derivatives exactly like you would in calculus 1. So again, you may need to apply a product rule or a quotient rule or a chain rule or something like this, right? But you just apply all those same techniques 3 times, once for each component. Likewise, when you take integrals, the integral here is that you just go along and in each component, you integrate. Looks like this is a definite integral starting at A and ending at B. So that's what we do for each one of these. So again, your functions need to make sense. They need to be integrable in order to actually integrate them. But assuming that they are, that they're not some like horribly nasty function, then this is how you would integrate a vector valued function. Now, technically, like it says, all of these rely on limits. All of calculus is a lot of limits. So for instance, when we talk about the derivative here, a lot of these rules that we have derivatives are based off of limits, right? They're shortcuts, but ultimately what this is some limit as h goes to 0 of r of t plus h minus r of t divided by h, right? And again, these would be vectors. And that limit as h goes to 0, just like this was, back in calculus 1, this is technically the definition of the derivative. And likewise, integrals. These also technically depend on limits, right? This is supposed to be a limit of Riemann sums. So you take the limit as the number of rectangles goes off to infinity, and you're summing areas of rectangles. Those rectangles are going to have heights based on your function. and they're going to have widths, standardized width, some delta t. Which again, as n goes off to infinity, these widths are getting smaller and smaller here. But just like, I mean, this is a calculus class. I mean, if you want to, you can get really into the weeds with all this stuff in higher level math classes, 300 and 400 level math classes. But we're going to be basically sticking with, just like we did in calculus 1, where we're going to be applying the rules that we know and love, product rule, quotient rule, U substitution, that sort of stuff. Yes. Yeah, so the star there is basically that you can choose any point in the ith interval. So you break up your interval from A to B into n subsections, right? And you enumerate them. So 0, 1, 2, 3, 4, 5, all the way up to n, right? And so you're talking about the ith one, right? I is going from 1 to n, and you're adding up these areas. So in the ith one, you have to choose a point to be kind of your representative point that you're going to take the height. In calculus 1, you quite often chose like the right-hand Riemann sum or the left-hand Riemann sum, which is where you always choose the right-hand side or the left-hand side of that subinterval. But you don't have to do that, right? There's also midpoint. There's also lots of these things. And in kind of the generalized version of this is that you really can choose any point because those subintervals are getting smaller and smaller and smaller. So that's what the star is that there is some freedom there, but it turns out no matter what you choose, whether it's left or right or middle or some random thing in the middle sort of deal, it turns out they all equal this left-hand side. So that's what the star is that there's some freedom, that it doesn't particularly matter what you choose. Again, technically, right? All in the technicalities here. Any questions about this before we see some problems? All right. Well, here's a typical problem that you could see. Here is a vector valued function. I would like to find the derivative, right? And so just like I mentioned, we're just going to go component by component and take the derivative of each piece. So you're expected to remember things like the power rule, right? So when you take the derivative of x to the n or t to the n, right? That n comes down, you reduce your power by 1. That's kind of a classic. Expect to remember certainly derivatives of trig functions. Derivative of sine should be cosine, stuff like that. And E, this one came up in calculus 2 here, at least at MSU. And there's a small chain rule going on, right? Because it's not just e to the t, but there's that 3 there. So the derivative of e is itself, leave the inside alone. Then we multiply by the derivative of the inside. So the derivative of 3t is just going to be 3. Of course, if I was writing one more line, I might bring that 3 out in front or something like that. But this is a perfectly fine and correct answer. Well, why don't we do one more, and then I'll ask if there are questions. We can also, same sort of game here, but now instead of taking the derivative, take an antiderivative, right? And again, we're going to do this to each piece and evaluate from 0 to pi. So let me give you maybe 30 seconds head start on this one. Take the antiderivative. Another 30 seconds or so, get as far as you can. You want to peek at the answer I've got, what I think is correct up here. All right, let's talk through this one. Just like there's a power rule for derivatives, there's a power rule for antiderivatives, right? So in this case, we need to increase our power by 1. So it goes t to the 4th, and then we now divide by that new exponent, the 4 there. Likewise, when we integrate sine, we get negative cosine, rather than when we took the derivative of it, right, you got positive cosine. The third one here is probably the most difficult. And I kind of breezed through it. I didn't really do a great job showing my work. So if I wanted to interject another step or two or so, what technique did I actually use on this third term here? What technique do you need in order to integrate this? Yeah, U substitution, I heard it. So yeah, there's really there's a small U substitution, just like when we took the derivative, there was a small chain rule. So this is fine here. Like if you were doing this on a quiz or an exam, this is an acceptable way to show the U substitution here. You don't need to kind of formalize it. So this is useful for you to know, right? Because you want to receive the maximum number of points on quizzes and exams. And if you're worried about, is this too many steps that you're skipping? The answer is no, right? But if you're not to this place yet, right, you can formally write out and take a little bit slower here and letting U be equal to 3t. And then du is going to be equal to 3 dt. And then this is the integral of e to the u. And instead of dt, I'm going to write du divided by 3. So that's where that 1/3 is going to be coming from. Then when you integrate e to the u, you get itself. And then you substitute back in, right? Instead of u, you put the 3t. So you're certainly allowed to include more work like this. However, as you're practicing, as you're doing web work problems and things like this, I think it's maybe worth your time to try to get a little bit faster at U substitution, trying to push yourself to get to this standard here, because it saves you some time on quizzes and exams if you don't have to write out each of these steps. All right. Well, now we need to plug in things and just be careful here. So plugging in pi and 0, and again, using your calculator can, especially for like trig functions and stuff like this, the TI-30 you get for the quiz and the exam, it's a good idea to kind of be carrying that around with you. And don't forget, sometimes when you plug in 0, you do truly get out 0 in the function, but there's other times when you plug in 0 that you don't get out 0. So a common mistake that I would see is sometimes people forget this, like -1, right? And that's coming from when I plugged in 0 here, I got e to the 0th power, and anything to the 0th power is 1, right? And so that's why I needed to subtract away that 1 there. But that's a common mistake that I see on quizzes and exams, especially under the stress, right? Is that sometimes people forget about plugging in both the upper and lower bound, especially when one of them is 0, right? People seem to like to skip that. Any questions on either one of these, the derivatives or the antiderivative stuff? Oh, sorry, yes.
Given the bound of the interval, put plus c for each of them?
Yes, and it'd be plus c for each term. So yeah, the question was if you don't have the bounds, like in this case, we had 0 to pi, but if it was just an indefinite integral rather than the definite integral, yeah, you would do plus c. And so you would need plus c in the first and the second and the third term. And then one little caveat, if you just write plus c, sometimes people will get confused and think you mean that it has to be the same constant. But in fact, they could be 3 different constants. And so you could do c, d, and e to denote like there are 3 different constants, right? The one in the first term could be different than the one in the second term. That could be different than the one in the third term. You could also do subscripts, c sub 1, c sub 2, c sub 3. Or if you're doing a indefinite integral, right, you could just do plus a c vector, right? And then that has components C1, C2, C3. So that would be equivalent as well. Good. Any other questions? Oh, sorry, yes. So yeah, we're going to get to that here shortly, but it's very similar to in our Calculus 1 days. So in Calculus 1, right, the derivative was something like slope at a point, right? So we have some interesting vector valued function. I don't know what exactly this one looks like, but we have some curve in space. And if you pick a point, right, you could ask what is the slope at that point. Now, slope's a little bit of a strange thing in 3 dimensions, right? When we're doing this with lines, instead of slope, we talked about a direction vector. So this will be akin to a direction vector. What direction is the curve heading at that point? So that's what the derivative is going to be. And the integral, likewise, you have some interesting maybe curve in space that maybe zooms around and whatnot. So x, y, z. And still you could talk about the area under this, kind of projecting it into the xy plane. And you could ask about how much area is still under that curve. No, it's not volume. We will get to volume, but that's going to be chapter 15. For volume, you need to start with a surface. And so since we're starting with just a curve in space, underneath it is just going to be area still. But if you started with an interesting surface, right, maybe like the surface of this table, you could ask about the volume underneath it, like maybe between the table and the floor or something like this. So yeah, we will certainly get to that, but that's going to be chapter 15. We need to develop surfaces first. Any other questions? Okay. Well then, moving on. A lot of the rules that you know and love about derivatives hold true for vector functions as well. So these are the classic rules from your Calculus 1 about taking derivatives. And you'll see that basically everything you want to be true still holds true. So if you have the derivative of two things being added together, two functions being added together, you are allowed to kind of break it up and take the derivative of one, then the derivative of the other, and then add those results. When you have a scalar, suppose c is 5 or -3 or something like this, right? You're allowed to it's just c times whatever that derivative is, just like in Calculus 1. What gets a little bit interesting is, well, we have lots of different products now that we have vector valued functions. So you could have like a scalar function times a vector valued function. And the claim is that the product rule still works. You could also have two vector valued functions, and in which case, right, the products that we have are dot products and cross products. And the claim is that those work as well. With a cross product, remember that the order matters. With a dot product, you're allowed to kind of do this in either order here. But for the cross product, it really matters that the u's stay on the left. Whatever's on the left should stay on the left. Whatever's on the right should stay on the right. Because for cross products, if you start flipping those, right, you're going to incur negative signs. And then finally, this is a chain rule, right? So the chain rule says, normally you would have the derivative of the outside, leave the inside alone, times the derivative of the inside. So a chain rule works here as well. The proofs of these things are pretty boring, I would say. This is a mathematical theorem. It has a proof, right? It's nothing that you have to take for granted or take my word on. I'll show you here a proof of C, for instance. I think C is maybe a mildly interesting one. And the book has a proof for D as well. But again, you're just going to kind of break this up in components. So maybe your U vector has components U1, U2, U3. And when we go and we take the derivative of this, well, first I'll go ahead and push my scalar function throughout the vector. And then I'm going to be taking the derivative just using the Calculus 1 product rule. So you're going to have the derivative of the first times the second, plus the first times the derivative of the second. And you do that 2 more times. And then kind of if you break this out and separate your vector in a clever way, you get exactly what we claimed here. So again, it's just basically kind of tricks of moving this function inside and then outside of the vector. So it's not very enlightening and whatnot. It's just kind of following and making sure you don't make any silly mistakes. So that's a sample of what the proof would look like for one of these. But let's see maybe how could we utilize this? What would be a likely question or something that we could see on homework, on quizzes and exams that kind of rely on this? So here I have a scalar function, and then I have a vector valued function. So my scalar function, apparently, when you plug in 1 into it, it outputs 3. And if you ask it what is its slope or what is its derivative at 1, it looks like it's decreasing, right? It has -4 for its slope. Then for my vector valued function, when we plug in time 1, it looks like it's at the point 3, 0, -5. That's where it's pointing. And if you were asked about its derivative or its direction vector, right? You get 0, 1, 2. So then the question is, well, what is the derivative of this at time 1? So remember, this is the Leibniz notation here. So this is evaluated when t equals 1. So evaluated at t equals 1. So that's what that long bar with the subscript means. Well, that's good because we know a lot of information about the function at time 1. So I'm kind of excited that we get to plug this in. So when I take the derivative, we're going to be using the product rule. Again, technically, this is based off of statement C here, where we have a scalar function and then a vector valued function. So this is saying that it behaves just like you would suspect from calculus 1. So we're going to have the derivative of the first times the second plus the first times the derivative of the second. And again, we want to evaluate this all when t is equal to 1. So let me go ahead and erase my t's here. And plug in everywhere I saw a t, I'm going to plug in a 1. So now we go and we read our information from above. We have f prime of 1 is supposed to be -4. U of 1 is supposed to be 3, 0, -5. F of 1 is supposed to be 3. And U of 1 is supposed to be 3, 0, -5. Sorry, U prime of 1. Bad job reading. 0, 1, 2. So why don't we go ahead and simplify this down as much as possible. I'm going to have -12, 0, 20 plus 0, 3, 6 once I evaluate out my scalar multiplication. Once I evaluate out my vector addition, I'm going to have -12, 3, 26. Something like this is probably not substantial enough to be like a free response style question on a quiz or an exam, but it could certainly make a fine multiple choice, right? And then of course you could have 4 other answers that don't work. All right, so that's showcasing how maybe you could use some of these properties. Any questions about this here? Okay. So then why don't we go ahead and enter into the second part. And this is, as I alluded to, this is kind of getting closer to the question about what does this physically represent? And so just like in calculus 1, the derivative was the slope of our function at a particular point on that function. Likewise, as I already kind of spoiled the surprise here, the derivative of our vector valued function, again, at some time here, say A, is the direction, all right, or again, kind of the direction vector. That our function is heading towards at this time. So again, you think of it as a slope. It's telling you the direction in which this vector valued function is headed. Another thing you can do with this, and we'll practice it a little bit here, but it gets used a lot in chapter 16, is this unit tangent vector. So unit tangent vector. Let me include up here. So this is also referred to as the tangent vector. So rather, you could say it's the direction or the direction vector. You could also say the tangent vector, because again, it's going to be tangent to our curve. So the unit tangent vector is going to be pretty much the exact same thing, but you need to make sure that it's a unit vector. So you're going to have your r prime of A, but in order to force it to be a unit vector, you're going to divide it by its magnitude. So something like this. Of course, you can combine the fraction to make it look all nice. r prime of A divided by the magnitude. So that's what the unit tangent vector is. And maybe I'll at least tell you, so in chapter 16 in particular, like 16.2 or so, we get things where we're integrating these vector fields, integrating a vector field, and it looks something like this. You get f dot t ds is the classic. So you're going to be integrating, this will end up giving you like work that the vector field is doing, pushing particles along your curve. So vector fields are going to be things like a gravity field or electromagnetism, right? Some magnetic field. And they're going to act on particles. And notice that we get this t here. This t is the unit tangent vector. So we're kind of doing a little bit of legwork now in order to be able to give ourselves some relief later on when we have to calculate out this quite complicated thing. So unit tangent vectors are a big deal, and they'll be coming back. All right, but for the time being, let's maybe calculate out a few of these here. So I'll take the easy one, this first one here, and then I'll give you guys a chance to maybe work on the second one. So suppose that I tell you that r prime of 5 is equal to 212. Find t of 5, right? So this is making sure that you know the notation, right? It doesn't say the unit tangent vector, it just says this t thing, right? So you have to know that that means the unit tangent vector. And so in order to calculate this out, unit tangent vector at 5, we need to take our vector, r prime of 5, 2, 1, 2, and divide it by its magnitude. So let's see, 2 squared 4, 1 squared 1, 2 squared 4, all added together, thrown inside of a square root. So that's going to be 2, let me write this as 1/3 times my 212. So again, this denominator is going to be the square root of 9. That's dividing by 3 there. Dividing by 3 is the same thing as multiplying by 1/3. And so if I want to make this as simple as possible, it's going to be 2/3, 1/3, 2/3. So again, usually for some of these simpler ones, I practice getting them into their simplified form. Just because if something like this did appear on a quiz or an exam as a multiple choice problem, right, it's very possible that they wouldn't give you 212 all divided by the square root of 9 here. They may simplify it, and one of your answers might be 2/3, 1/3, 2/3. And so you need to know, even though maybe what you have isn't exactly what's on the page, right? But if you simplify it, maybe you can get something that is. So it's a good habit to simplify this a little bit, especially for things that could appear as multiple choice problems, right? Then you have to know if your answer is equivalent to one of them on the page. All right. Well, like I promised, that was the easier one. Here's a more complicated one, right? Instead of r prime, I'm giving you r. And I would like you to find the unit tangent vector when t equals 0. So please take 90 seconds or so, head start, and get as far as you can on this one. You can see I'm testing your derivative skills a little bit more too. All right, let's see maybe if we can solve this one together. So for some of these that are a little bit longer, sometimes I do like to break it out literally as 3 different problems, right? So I need to ultimately take the derivative of these 3 functions here, and then I'm going to need to put them all aside a vector, right? So, okay, the third one, quite easy, right? So the derivative of 2e to the t, well, 2's along for the ride, and you take the derivative of e, you get itself. Yeah, so the second one requires you to kind of remember something. In the similar vein that you need to remember that the derivative of sine is cosine, this is also kind of a popular inverse trig function, probably the most popular of the 6, that is really quite useful, as you saw maybe in your calculus 2 days. And so it's worthwhile not to completely forget about what its derivative is. Anyone happen to remember? What is the derivative of this thing? Yeah, you got a guess? It is, yes, that's exactly right. This came up a decent amount in the partial fractions. Again, we're not going to be doing partial fractions with this, but it is kind of a very popular one. So a good thing to remember there. Okay, and in the first case, there's going to be 2 rules that we need to apply here. And so like each individual part of this isn't particularly complicated. It's just kind of the accumulation of everything. Can anyone tell me maybe what is one of these rules that we need to apply in order to find the derivative of this? Yeah? Product rule. So that's going to be the first thing that should be looming on your mind, is that because there's a product of functions, right? T times e to the negative t. So this outermost operation is that there's a product. And so if I was to think about, okay, let's take the derivative of this, I would need to do the derivative of the first times the second plus the first times the derivative of the second. Now, the derivative of e to the negative t, right? If you'd like to, you can even break this out into a, you can say, well, I'm going to take the derivative of this. Just give me a second, right? You could just write that. But the derivative of e to the negative t, it's like very similar to e to the 3t, right? When we took the derivative of this, there's a small chain rule going on because it's not just e to the t, it's e to the negative t, right? So when I take the derivative of this, if I was to evaluate this, we'd get, a copy of itself, so e to the negative t, but then you need to also multiply by the derivative of the inside. So the derivative of negative t is going to be -1. So you get this extra negative sign. So let's go ahead and maybe write this as e to the negative t minus t e to the negative t. That's maybe as simple as I can write that. All right, so I've solved the derivative for each one of these pieces. I could take that and I could say that this is what r prime of t is going to be equal to. Put those all together. But remember, I want to evaluate this when t is equal to 0. So ultimately, I'm going to be plugging in 0 for these things. So maybe, so I don't have to write so much, let's just go right to when I'm plugging in 0 for all of the t's. So in my first component, which again came from the derivative of this thing that I needed to use the product rule on, I'm going to have e to the negative 0, that's 1, minus 0 times, who cares, right? Again, I'm plugging in 0 for t. So the fact that there was a t kind of on the ground level there, that takes care of the second term, second bit there. Okay, for my second piece, I'm going to have 1 over 1 plus 0 squared. And then for my third piece, I'm going to have 2 times e to the 0, which is, again, 1. Now at this point, this is exactly the same as our previous problem, right? Again, our ultimate goal is to find the unit tangent vector at 0. I now know that this derivative vector is 1, 1, 2, and I'm going to need to, in order to make it unit, divide by its magnitude. So maybe 1 divided by root 6, 1 divided by root 6, 2 divided by root 6. Any questions on this one here? Yeah. Yes. 2t e to the power t. So you're asking about for this one here, right? Or oh, okay, just probably a misreading thing. Yeah. Good. Any other questions? All right, so I guess the other thing that I want to point out, so if something like this was to appear on a quiz and exam, let's imagine this is a standard response style question, something like that. Because I saw some of you, you were able to get one or two of these quite quickly, right? I would encourage you again to think about trying to maximize your partial credit, right? And so even if you don't know how to do all of them, right, still continue, do the ones that you know how to do, and then just kind of make something up for the third one, right? So suppose you can do 2 out of the 3, right? So make something up for the third one, but continue and see this process all the way through. Because if you just say, well, I don't know how to take the derivative of t times e to the negative t, so I'm not going to do this problem, right? You're going to get 0 points rather than, right? If you kind of know how to do the other 2/3 of this, right? You could very well get 2/3 of the points. So if you think about trying to maximize partial credit, especially when it comes to quizzes and exams and whatnot. Yeah.
I noticed this is kind of just a general thing that you didn't define the quotient rule. Is it the same as the quotient rule for just regular derivatives? Like
In the table above. So we have a chain rule and we have a product rule. So that's typically how you would define the quotient rule, right? And so because when you divide by something, it's just raising it to the negative first power. So between the product rule and the chain rule, you could recreate something like this. We don't have quotients of vector valued functions like we have products of vector valued functions, right? So we have a dot product and we have a cross product, but we don't have any quotients when it comes to how do you take one vector and divide it by another vector. It turns out there's not really valuable ways to define that. You could certainly divide by a scalar function, but again, then you could just use the product rule and the chain rule. All right. So lastly, thinking about another type of integration style problem. Back in Calculus 1, you sometimes got problems that look like this. It would say things like, if f prime of x is equal to 2x and f of 1 is equal to 3, find what you started with, find f of x. An alternative way to phrase that is solve the initial value problem. So I'm looking for some function f of x that satisfies when you take the derivative of it, you get 2x, and when you plug in 1, you ought to get out 3. So you're trying to find some function, right? Even though this statement right here doesn't say what you're exactly finding, right? With the solve the initial value problem, this prompt means find f of x, find the function that satisfies these things. So of course, the way that you probably did this back in your Calculus 1 days is, well, you have the antiderivative that's good at undoing derivatives, right? So I have 2x, this thing's supposed to be the derivative. So if I apply the antiderivative or the integral, I'm going to get something that, again, kind of undoes this, and this is a good candidate for f of x. But again, whenever you do an indefinite integral like this, you should have plus some constant of integration. Because not only does x squared, when you take the derivative of it, you get out 2x. So certainly, yes, if you take the derivative of x squared, you get 2x. But also, if you take the derivative of x squared plus 5, right, you also get 2x. Or if you take x squared minus 13 and take the derivative of that, you also get 2x. So really, plus any constant here, when you take the derivative of that, you get 2x. So that's where that plus c is coming from again. And notice we want to choose a good plus c, so that way, if I plug in 1 into this, I ought to get out 3. So again, this right here is my candidate for f of x. I undid my derivative, thanks to the antiderivative or the integral. And I want to choose a good c here, so that when I plug in 1, I get out 3. So if I plug in 1, I should be getting out 3. And this tells me that the constant that I want to choose, this plus c, is 2, right? I can rearrange this and get 3 minus 1 is 2. And so the function that I'm interested in is x squared plus 2. Notice that if I take the derivative of that, I get 2x. And if I plug in 1 as it stands, and it's just 1 into f, not f prime, 1 into f, right, I should get out 3. So that satisfies both of these things. And so this is the solution to my initial value problem. In calculus 3, we're going to play a very similar game. Here is a similar phrased problem. I give you a derivative and some other point. In this case, when you plug in 0, you ought to get out the vector 4, 2, 3. So with this information, my question is, well, what was the function that I started with, right? What does R of t equal? And we solve this very, very similar to the way that we solved this in calculus 1, except for you're going to do it 3 times, right? 1 for each component, the I component, the J component, the K component. So we're going to go ahead and integrate our derivative to 2e to the t and root 3t plus 1. When I integrate that, so integrating 2 is going to give me 2t. Integrating e to the t is a copy of itself, and 2 is along for the ride. And then finally, integrating a square root. And again, there's a small u substitution here, right? Because it's not just the square root of t, but it's the square root of 3t plus 1. So again, we're getting good at u substitutions. Small u substitutions can save you some real time. So when I see this, I think about, well, square roots are the same thing as the 1/2 power. So if I was to integrate this, I would have to increase my power to 3/2. Right? In order to, right, when you undo this, you would have that 3/2 come down. So again, this is me just applying the power rule here. So I'm going to have the reciprocal there. And then because of this extra 3 here, if you imagine taking the derivative of this, you would have this 3 popping out. And so you need this extra 1/3. Again, if you spend some time practicing this, this is quite reasonable for you to do as well. But in the meantime, right, if you want to, and if it was on a quiz or an exam, and if you're nervous and you're hesitant and the clock's ticking down and all that sort of stuff, right, you could do u is equal to 3t plus 1. So this is integrating root u, but I need to switch out my dt for some number of u's here. So I guess I should write down that du is equal to 3 dt. So instead of dt here, I'm going to write du divided by 3. Now when I integrate this, this square root of u becomes this u to the 3/2 times 2/3. And again, this extra 1/3 is along for the ride. Plug back in your u, and you have exactly what I had here a little bit faster. All right, but just like in our calculus 1, and it was already asked, in fact, right, that you should have plus a constant of integration. But the constant of integration doesn't need to be the same for each one of these things. So you can either do a plus constant vector, or you could go along to each piece here and do maybe 2t plus its constant, 2e to the t plus its constant, and then what this is 2/9, 3t plus 1 raised to the 3/2 plus its constant. But again, they can be 3 different constants. And so you can name them C, D, and E if you'd like, or you can name them with subscripts, but somehow you have to know that these are possibly different. So, okay, we have our first condition met. The other condition is that when you plug in 0, you ought to get out a specific vector. So you ought to get out 4, 2, 3 if I plug in a 0 for my t. So that would be C1, 2 plus C2, and this would be what, 2/9, 0 plus 1, 1 raised to the 3/2 would be 1. So that'd be that plus C3. So my C1, C2, C3, right, if I was to go ahead and maybe start subtracting this and trying to solve, I would have, well, C1 is just equal to 4. I like that. That's simple enough. It looks like C2, when I subtract 2 from both sides, is going to be 0. And then I have 3, that's the same thing as 27/9, I suppose, minus 2/9. So that's going to be 25/9. So now that's what I need to plug in for, again, my C1, my C2, my C3, and then that will be my final answer. So I'll finish that up really quick here, but I see that we're out of time, so apologize for rushing a little bit. So 2t plus 4, 2e to the t plus 0, and then 2/9, 3t plus 1 raised to the 3/2 plus my C3, which was 25/9. So this right here is my vector valued function, my R of t, that satisfies when you take the derivative of it, you get what it wants. And when you plug in 0, you get what it wants. In this case, the vector 4, 2, 3. Okay? So this is an example of initial valued problems. Now I just basically need to do them 3 times. So I have one for you to try. Please give this a go on your own, and I will post the solutions to it on D2L by 4 o'clock today. All right. Well, thank you very much, everyone. And good luck on the quiz tomorrow. And I will see you on Friday. Stick around if there are any one-on-one questions.